Good morning. Now, this is class 4 of our module 4 varying currents. Now, I hope in the last class we have studied about uh, AC circuit containing only resistance, right? That is, we studied about how EMF and current varies in an AC circuit containing only resistance, and we have seen that in an AC circuit containing only resistance, both EMF and current are in phase. Now today we will discuss about AC circuits containing only inductance and AC circuit containing only capacitance. Okay, so let us begin and let us see how current and EMF varies in these circuits. It is quite simple. Once you study that is, if you study inductor, then it in a very naturally you can write the circuit containing capacitor, because the description and the way of proceeding of the derivation, everything is the same. The only thing is that there will be a slight changes in the expressions used. Okay, now let us begin with a circuit containing inductor only. See, this is an AC circuit containing only inductor. This is the EMF that we are applying. It is of the form E equal to E0 sin omega t, and this is the inductor, that is, it is represented by the letter L. So here you have an AC circuit containing only inductor and you are applying an EMF or voltage E0 sin omega t. So in order to oppose that applied EMF, this inductor will produce a back EMF or an opposing EMF, and its magnitude is of the order of L di by dt. So as per Kirchhoff's law, they will nullify each other, that is, the EMF that we are applying, I already told it is E0 sin omega t. It is opposite to that of the opposing EMF produced by inductance coil L, that is L di by dt. So the net effect will be E0 sin omega t minus L di by dt will be 0. So from this equation we can find I di. How? Just rearrange this equation. So you will get di as this, and on integrating you will get on integral di will be I, then E0 L integral sin omega t. You are taking integral on both LHS and RHS. I is kept as such. E0 by L is also kept as such. Now what is integral sin omega t? Minus cos omega t by omega. It is written here. Then next is E0, this omega is taken outside, so it will be E0 by omega L minus cos omega t is kept as such. Then here also E0 omega L is kept as such. Now cos omega t is can also be written in this way, that is cos omega t is sin omega t plus pi by 2. So since here it is minus cos omega t, we can write sin omega t minus pi by 2. Okay, then this E0 by omega L, it is actually the peak value of current or the maximum value of current. So it is expressed by using this letter I0. So I0 is actually E0 by omega L. Sin omega t is kept, omega t minus pi by 2 is kept as such. So from this expression, you can definitely say that in an AC circuit containing only inductance, what happens to the current? Current always lag behind EMF, that is current always go behind EMF by a phase angle pi by 2. Why you say it lags? Because here you can see a minus sign. Okay, that is why we say that in an AC circuit containing only inductance, current always lags behind EMF by a phase angle of pi by 2 or 90 degree. In other way, we can say that because of this back EMF, the flow of current limits initially, that is when EMF is maximum, current is 0. When EMF is 0, current is maximum, like that. So just remember this, that when in an AC circuit containing only inductance, current lags behind EMF by a phase angle of pi by 2 or 90. Now let us see about this diagram. This is a phasor diagram. Here you can see this is the peak value of current, peak value of EMF. Here you can definitely see that current is lagging behind EMF by a phase angle pi by 2. Now this is a corresponding phase diagram. See, this is the current and EMF is going the whole way long. So this current is lagging behind EMF by pi by 2. So you can draw this figure also, both this sine wave form as well as this phasor diagram. Then let us see about what is inductive reactance. I already told that the peak value of current, that is E0 by omega L, we replace it by I0. Okay, that is the peak value of current. So we can say that what is inductive reactance? The definition is that if the inductive reactance is nothing but effective resistance offered by the inductor to the flow of AC. Okay, so inductive reactance is defined as the effective resistance offered by what? The inductor which is present in the circuit to the flow of AC. That is, this inductive reactance is represented by the letter XL. So XL can also be written as omega L. Omega is actually 2 pi f, right? So it will be again 2 pi fl. What is F? Frequency of alternating current. So from this you can see that this XL or inductive reactance is directly proportional to frequency f. So for a DC, that is for a direct current, we know frequency f is 0. So XL will be 0. So for a DC current, this inductive reactance FL is 0. Okay. Now this is a graph that shows the variation of XL and F, that is inductive reactance versus frequency. It is a straight line. So these are the things that you have to write when you are asked to discuss about an AC circuit containing only inductor. Okay, hope it is clear. Now the same procedure we will apply. There will be a slight changes in the expressions when we discuss about this circuit containing capacitor. Everything is the same. The procedure is exactly the same, but the only change is a slight change in expression. So once you study inductor circuit correctly, it will be very easy for you to study capacitor circuit. Okay, now see, here you can see a circuit containing only capacitor. This is the EMF that you are applying. This is a capacitor C. Now let the charge on the capacitor be Q. It varies continuously as applied EMF and the corresponding current flows in the connecting leads. So in the case of an AC circuit containing capacitor, the EMF that we are applying, that is E0 sin omega t, will be equal to the applied EMF. So Q by C is nothing but Q is the charge on the capacitor, C is the value of capacitance. So this is the potential or the EMF that is developed across the capacitor. So the applied EMF, the instantaneous PD across the capacitor plate, that is this one. The instantaneous or the potential difference across the capacitor, that is Q by C, will be equal to the applied EMF. So this is the expression. So from this you can find, by rearranging the equation, you can find the value of Q. It is nothing but C E0 sin omega t. But we know that I or current is the rate of change of charge, that is dq by dt, right? So d by dt is kept as such. Now here this Q, instead of Q we have this expression. So you are writing this expression here. Then from this d by dt of C E0 sin omega t will be, C E0 is a constant, so it's taken outside. Then what is d by dt of sin omega t? Cos omega t omega. Okay, so you get that equation, omega C E0 cos omega t. Again we are just arranging this again in a convenient way, that is E0 is kept as such. Then omega C is written as E0 divided by 1 by omega C. This E0 divided by 1 by omega is the same as omega C E0. So you are just rewriting this in this form. Okay. Then cos omega t. Cos omega t I already told, it can be written as sin omega t plus pi by 2. Now here this one is the peak value or maximum value of current. So E0 by 1 by omega C can be written as I0. So I will be I0 sin omega t plus pi by 2. So here you can see that a plus sign appears, right? here there is, you can see a plus sign. In the other case, in the inductor case, you can see a negative sign. That's why we said that current always lag behind EMF by pi by 2, right? In an inductor circuit, here in place of this positive sign you have a negative sign, so we said that current always lag behind EMF by a phase angle of pi by 2. But here, in the case of an AC circuit containing only capacitance, you can see a positive sign. So we can say that in a AC circuit containing only capacitance, current lead EMF. See, current lead EMF by a phase angle of pi by 2 or 90. This means that rate of flow of charges is high initially. It gets saturated at a maximum value. That is, current reaches its maximum value when EMF is 0 and reaches its minimum value when EMF is maximum. Like that, just the reverse. So similarly, similar to what we have seen in inductor case, here also you can see a phasor diagram and a sine wave diagram. Here this current is leading EMF by pi by 2. This is a phasor diagram. So these two diagrams also you can draw. Similar to inductive reactance, here you have capacitive reactance. Now, what is capacitive reactance? It will be the effective resistance offered by the capacitor to the flow of current in an AC circuit. It is expressed by the letter XC. It is 1 by omega C. Omega is 2 pi f, so it will be 1 by 2 pi fc, whereas f is a frequency of alternating current. Now let us see, here you can see that this capacitive reactance Xc is inversely proportional to the frequency of alternating current f, right? So for a DC circuit, DC current, we know frequency f is 0. So what is capacitive reactance? If we put f 0, in this case 1 by 0, 1 by 0 is infinity, so Xc is infinity, right? That means for a DC circuit or for a DC current, capacitive reactance will be infinity. Okay, that is the circuit offers infinite reactance for the flow of DC. And here this is the graph that shows the variation of capacitive reactance with frequency. It has the shape of a hyperbola. And here this we have already discussed, that is capacitive reactance is infinite for DC. Why? Because for DC f is 0. That is why we say that capacitor blocks DC. Now reciprocal of reactance is called susceptance. Its unit is ohm inverse or Siemens. Okay. So we have studied about AC circuit containing resistance, inductance and capacitance. How was the nature of variation of EMF and current in the case of an AC circuit containing only resistance? That is, in an AC circuit containing only resistance, current and EMF are in phase. In an AC circuit containing only inductance, current lag behind EMF by a phase angle of pi by 2 or 90. In an AC circuit containing only capacitance, current lead EMF by a phase angle of pi by 2 or 90. These are the differences. Now we are going to consider an AC circuit containing both, that is both inductor L and resistance R. Okay. So here let VL and VR be the potential difference across. VL is the potential difference across L. VR is the potential difference across R. This is the EMF that we are applying. So this is the corresponding phasor diagram. That is, here VL and VR are mutually perpendicular. Okay. Now we will derive the expression. Resulting EMF will be that is E square will be VR square plus BL square. You know VL E square is kept as such. VL is equal to IXL, that is V is equal to actually current into resistance, right? So potential difference across inductance L will be current I into XL. XL is actually a sort of resistance. It can be called as what? Inductive reactance. Okay, so you are substituting that value here. E square equal to VL is IXL. So it will be I square XL square. Then what is VR square? I square R square. Okay, so I square is common, it's taken outside, everything is kept inside. So I will be E by root of R square plus XL square. Now this root of R square plus XL square is actually the effective resistance of the circuit, and it is represented by the letter Z called impedance. So Z impedance equal to square root of R square plus XL square, and so this is again equal to root of R square plus XL, you know it is omega L the whole square. We already studied that inductive reactance XL is omega L and the capacitive reactance XC is 1 by omega C. Okay, now here Z is measured in ohm. Now the reciprocal of impedance is called admittance. Its unit is Siemens. So here it should be noted that the current I lag behind EMF by a phase angle phi, and that phase angle is given by tan phi is equal to VL by VR. We know VL is equal to IXL and VR is IR. I and I get cancelled. So tan phi will be XL by R. Again XL is equal to omega L and R is kept as such. So tan phi is equal to omega L by R. So from this equation it is clear that phase angle depends upon value of inductance of the circuit. Now if this L is 0, then phi will be 0, then the circuit will act as a pure resistive circuit. Now on the other hand, if R is 0, then phi will be 90 and the circuit will act as a purely inductive one. So you know this phase angle phi actually depends upon the value of L and the value of R present in the circuit. So there is nothing much difficult to learn. Hope you understood the difference, and so just study one and then you will definitely understand the other, because there is not much complications. So please go through it. Okay, that's all for today. Thank you.